For the last 20 years, we can say that the Wi-Fi networks have changed completely, entirely. Wi-Fi started, as many of you know, as a best effort network and not used for critical applications. So nowadays, Wi-Fi is completely critical and is for real-time applications, for streaming, and we can say that it's the primary source of internet connectivity. For this main reason, we cannot assume that the Wi-Fi is to be turned on and used. It needs to be well planned, installed, and tested before going into production, okay? Currently, the Wi-Fi connection of our smart devices is essential part of our daily lives at home, at the office, whatever. For this reason, we have all felt intrigued by knowing the reasons that cause our device to disconnect from Wi-Fi for no apparent reason. Okay, so in this first slide, we're going to talk about the 5 most important variables that we should consider in order to have a good Wi-Fi experience in any environment. So it is not only a matter of the AP brand or the switch brand that we are using. It is a set of many other things that will define if the Wi-Fi behaves well or not. Okay, so the first point here is the quantity and the type of antennas. It is clear that we do not use the same type of antenna in a Starbucks or in a 7-Eleven store than in an office or in an auditorium. Depending on the needs and the spatial flows that the user needs, we're going to define, and obviously the quantity of devices and users, we're going to define the AP model. Usually in certain areas, we put 2x2 APs. In other areas with a higher flow of users, we normally put 4x4 or 8x8. And in others, we used to put 2x2 or 4x4. In other words, we do not use the same type of AP for the entire project. In customer, for example, like warehouses in Sam's Club stores or Costco stores or Walmart stores, where the ceilings are very high, it is necessary to put APs at least 4x4, like the Arista C130. So with this type of AP, we can ensure that the signal can reach more than 8 meters. That is the height from the ceiling, okay? The second point here is the quantity of users. I will put here a very typical example for us, that is a university. A university, it is clear that does not have the same Wi-Fi needs as a store or a hospital or an airport. For example, in a university before the pandemic, we could say that a student carried at least 3 devices to the university: a smartwatch, a smartphone, and a Mac. So in the case again of a Costco store, the network administrator or the marketing guys obviously are not interested to give connectivity to the users to more than one single device. If we go to a hospital example, for example, you know that the hospitals have IPPBX with wireless phones for doctors, for nurses. They have many IoT devices there that obviously requires Wi-Fi connectivity. So in this case, you also will have many devices and many users, okay? So the point here is we need to have a real definition on the number of the devices in order to get the maximum concurrency, the number of simultaneous devices that we can have in that environment. The third point is also critical, is the bandwidth and the application control. Imagine how the network would be in a university if all the students are streaming the Champions League or the NBA or content that is not academic. So it is obvious that the quality of the Wi-Fi would be very poor, very bad. It is completely necessary in all the environments, put bandwidth restrictions and application control in order to ensure the quality. And there are some other environments that we need to restrict the streaming because the bandwidth is very limited, okay? The fourth point is the cabling. If we need to ensure at least 100 megabits per second per AP or per user, we would need to use at least cabling 5E or 6, or even if we want to implement Wi-Fi 6 project in a new campus, we need at least Cat 6 for our cabling, okay? Finally, the fifth point, the last one, is very critical, is all the switching portion, the access, the aggregation, and the core. It is useless to have APs with Wi-Fi 6 if we have uplinks in 1 giga. The entire network needs to be adequate with 10 gigas at least, from the PoE leaves, from the APs, and after that the PoE leaves, and after that the spines. Otherwise, the bottleneck will now be in the switching side. Okay, so the network also needs to be prepared for failures. And there are many customers, as you well know, that are still using stacked switches, so which is a problem in terms of scalability, stability, and in the there is a limitation in the quantity of switches that you can have in one stack. So in this part of the slide, on the right side, we can see the physical barriers generated by the construction materials. Okay, so it is clear here that the materials that generate most attenuation or interference are concrete, are steel, and are basically mirrored. In the case of the metal or the steel, the Wi-Fi signal is absorbed, so this becomes a problem if the proper site survey was not done. Okay, and in the last part of the slide here, there are basically some specific things that we can have at home. Okay, that can generate interference for our Wi-Fi. So it is recommended to move all those devices that are microwaves, refrigerators, cameras, garage door openers, away from our AP. So in this way, we can have a faster Wi-Fi in our homes. This is the most typical problems that we can have in terms of Wi-Fi in the different verticals or different scenarios. The most common problems are basically low speed, lack of coverage, and disconnections. Let's start with the first scenario, that is a hotel. As you know, there are certain type of hotels like Holiday Inns or sleeping hotels with very specific formats. 3-level hotels with 15 rooms on the left, 15 rooms on the right, and with a central corridor. Normally, what happens here is that the people used to put the APs in the middle of the corridor. And what happens when there is a guest in each room? The Wi-Fi does not work. There are users who simply cannot associate to the AP. The second one is the universities. So it is also a typical case that there are areas where the connection is lost, or classrooms where the coverage is very low because someone decided to put, maybe for lack of budget or for a bad decision, to put an AP to connect to different classrooms. So that is also a problem. Warehouses, this is also a very typical case now. Imagine Amazon or Walmart warehouse right now in the middle of the pandemic with thousands of orders to be delivered every day, and with handhelds disconnecting for not having done a correct site survey. This is a very typical case. The hospitals, we talked about that some minutes ago. Basically, you have high voltage rooms, you have many devices that can generate interference with the Wi-Fi because some of them work in the same frequency in the band 2.4. The retailers, I talked about this. There are many guys at the store, and some of them can have disconnections, and then basically the problem of the height is an issue. Okay. The stadiums is a very complex also scenario at half times or at times where the people used to go for a beer or for a snack to the cafeteria or to the bar, to the pub. These points are usually saturated, so sometimes they'll launch also promotions in the screen so that the people can connect to the Wi-Fi and participate in a trivia or in a contest in order to win a gift. So also this creates saturation in the Wi-Fi. There are many other typical cases as airports or maybe transportation that is also very common. It's very common there to see APs burn out due to the voltage variations or high temperature. And this happens because the AP was not defined correctly or the way to power it, okay? There are many common. So the idea, this is also a clear images that have or show how bad installations look when they are not supervised, or sometimes when the people do strange things. Like here, the people is covering an AP with aluminum paper. I don't know why. There are also some scenarios, for example, this one or this one, with the telecom sites, when the APs are installed above the ceiling or the cable ladders go behind on the racks, obviously there the AP won't work very well, okay? According to ICAHAO, this slide is very technical, and the idea here is just to explain in a general way what happens here. According to ICAHAO, there is a life cycle in each Wi-Fi network that basically has 4 different phases. The first phase is basically the red section, that is the definition. And let's talk about this very quick. The define is basically the planning step that requires understanding of what the system needs to do. And we have here 2 general of requirements. The functional requirements, that is basically what does the system have to do, and the constraints, what does the system have to work around. The general requirements we can are here basically the usage. What is the purpose of this Wi-Fi network? How many SSIDs are we going to have? 1 for guests, 1 for staff, 1 for voice. We're going to implement WIPs for security. Which network appliances are going to connect to the Wi-Fi? The second one is the coverage. There is a requirement to provide coverage in all the locations of a facility where the Wi-Fi devices and applications are to be used. So this requirement made to be very straightforward, but is influenced heavily by 2 different types of constraints also, physical constraints and logical constraints. The physical constraints are basically the facility. How is the facility? If it's a new facility, a new building, can often be run inexpensively before the walls are fully erected and sealed. In a used building or an existing facility, running new wiring can be often be extremely challenging and expensive. In the logical constraints, basically, these are imposed by the owners or the operators of the facility. The largest of these is generally budget, aesthetics, and especially in high-end properties can be a major factor, okay? The third point here is the capacity. As I explained it in the first slide, the number of the simultaneous devices and the average and the peak traffic loads expected in the network is a critical factor. In high capacity areas such as classrooms, conference rooms, or arenas or stadiums, 1 or few APs can be more than sufficient to provide coverage. The point is, multiple APs could be needed in order to handle the high number of traffic volumes and devices, okay? The last point is the control. Obviously, we need to define how the authentication is going to work in this network, the association, the access control, encryption, roaming, and some other things. So let's go with the second phase or the second section, that is validation or design. Once all the requirements and constraints are quantified and well-defined, an appropriate design solution can be determined. So we need to understand here which type of access points are we going to use and which type of antennas. And also, obviously, all the aesthetic constraints that also may limit the quantity or the place where the APs can be put, okay? The third section is the deployment. Basically, this is the physical installation of the entire network, including APs, cabling, and switches. The complexity may depend on the size of the building, obviously, and as I said before, if it's a new building, it's less complicated. If it's a replacement of existing installed base, where old wiring and old Wi-Fi system or old switching is present and needs to be removed, so this will have more complexity due to the migration of the services. The last point is the monitoring or the diagnose. I don't know if you have heard about this concept, but there are MSPs. Many companies call it MSPs, are in the business of designing and deploying Wi-Fi networks, but also in maintaining those networks. So MSPs make money by having customer space support contracts, but these are only profitable if the network is working and the customers aren't actually calling every time for support issues. So the message behind this slide is that The design of a high-performance Wi-Fi network is complex engineering task subject to ever-increasing demands on the requirements and constraints. As such, design processes and measurements tools are necessary to identify and validate best practices in Wi-Fi design. So the troubleshoot problems in the existing deployments and the maximization of the performance are something constant in the networks, okay?